Okay, so welcome back to another video. So in today's video we have a little proof that we want to show. So we want to prove the following formula over here. Capital F sub n is equal to phi to the power n minus 1 minus phi quantity to the power n divided by the square root of 5. And keep in mind that capital F sub n is known as the nth Fibonacci number. And this whole thing actually has a name to this formula. Just keep in mind that phi is actually the golden ratio number, 1 plus the square root of phi divided by 2. Anyway, this little formula over here is known as Bennett's formula for Fibonacci numbers. And so what that says is that it's an explicit formula to help you, that is used to find the nth term of the Fibonacci sequence. And it's really interesting to see that there's a correlation with the golden ratio too, especially because if you take the two successive terms together and you take its ratio, it's actually approximately close to the golden ratio number. It's just really has no correlation with what we're really trying to do, but it's a really interesting fact to bring up. Really, this whole premise of this video is just to prove the following formula. So basically, we just want to make some observations and then rewrite some terms, or not really rewrite the terms, but also like manipulate some powers with the golden ratio number itself, and then use some algebra and manipulate things around as well. Let's start by discussing that the following equation, x squared minus x minus 1 is equal to 0. Okay, so this little quadratic polynomial is very important because this is what helps find the golden ratio solutions. So you see that if we were to find our solutions x, we see that x is equal to, and I'll take the, simply you can't just unfoil this, it's a little difficult, so we'll have to actually use the quadratic formula. So let's see, negative b, so this will be positive, so plus or minus the square root of, so let's see, this is negative 1 square, subtract that with 4, multiplied with a, so that's 1, multiplied with c, negative 1, and then I'll just divide this with 2 times a, so that's 1, and so therefore we have our two solutions. X is equal to 1 plus, let's see, 1, and then that's 1 plus the square root of 5 divided by 2, which that's actually simply just equal to phi. And then we also have another solution that x is equal to 1 minus the square root of 5 divided by 2. And actually, in other words, that's actually equivalent to 1 subtract with the golden ratio number. That's pretty dandy and all, so we'll just use these little two notations over here with the values, and then we're going to manipulate some stuff here. So let's start out first with just the golden ratio number itself, phi. So what I'll do is that I'll actually square both sides of the equation over here. So phi square is equal to 1 plus the square root of 5 divided by 2. That's square. And so if I do this, I get that this is equal to, let's see, so I'll actually do the direct calculation by hand. So square root of 5 divided by 2, then 1 plus square root of 5 divided by 2. So then I get that, let's see, we actually just performed the FOIL method. This is 1 plus 2 times the square root of 5, and then plus 5 divided by 4. Okay, so we add the terms together, so this is 6 plus 2 times the square root of 5 divided by 4. And really this is, simplify some stuff out, this is just 3 plus square root of 5 divided by 2. And in other words, this is actually can be rewritten as 1 plus the square root of 5 divided by 2. And then we add a 1 to it. And we know that this is actually the golden ratio number, so this is 5 plus 1. Okay, so that's, thus we can conclude that, thus phi square is equal to 5 plus 1. And it's actually a really interesting property with the whole golden ratio number itself, so it's really interesting if you ask me. So next thing I want to do is let's actually multiply a phi to the power n minus 2 to both sides here. Okay, so we have phi square, then multiply with phi to the power n minus 2, then that's equal to, let's see, phi plus 1, then phi n minus 2, So then this is going to be, here, I'll just keep going over here. So let's see, 2, 2, so that'll cancel, so we're just left with phi to the power n, and then that's equal to, so we just distribute over here, so this is phi to the power n minus 1, and then we add this with phi to the power n minus 2. Okay, so now let's actually start like putting some terms in. We'll start with just 1 and then go our way up. We'll just start with natural numbers for now. Okay, so if I plug 1, so I get, let's see, phi to the power 1, and so that's equal to, let's see, first, before I do this, let me just underline this little explicit formula we have over here. So if I plug 1, so I get that this is 1 minus 1, then plus phi n minus, or oops, this is supposed to be 1 minus 2. So then that's just, let's see, so phi to the power 1 minus 1, 0, so this is just 1, and then plus phi to the power negative 1, which there's actually a little interesting property that 1 over phi is actually equal to just phi subtract with 1. And so you'll notice that the equality actually equals each other because the 1's cancel from each other. So this is just phi. Now, next, let's start off with 2. So then this is, let's see, 2 minus 1, and then plus phi, then 2 minus 2. So that means phi 2 minus 1, that's, so that's just phi, of course. And then plus 2, so that's just plus 1. Kind of makes sense to say that because we actually just showed that from over here. So let's go to 3. 3, so let's see, 3 minus 1 plus, and then 3 minus 2. We said that this is phi squared, so that means this is just phi plus 1 over here, and then plus phi, which is just equal to 2 phi plus 1. Okay, nice. Let's go to 4, then 4 minus 1 plus phi, 4 minus 2. Then we get that, let's see, this is 3, so that means we showed that this is actually 2 phi plus 1, and then plus, add that with phi, phi plus 1. Therefore, that's actually just equal to 3 phi plus 2. And let's actually just do one more and see what happens. We'll do 5, then 5 minus 1 plus 5 phi minus 2. Okay, so 5 minus 1, 4. We said that that's equal to 3 phi plus 2, then plus 5 minus 2, that's 3. So this is 2 phi plus 1. Add the terms together, we get 5, 5, phi, and then plus 3. Now, that's nice and all. And let's actually recall a little definition of the Fibonacci sequences on how it's defined for like the nth term. So the following for Fibonacci numbers is defined as the following. So we actually have 4 different answers part of the systems. So the first one is that f sub n is actually equal to f sub n minus 2, or f of n plus 2. And I subtract that with f of n minus plus 1, then it's 0, then 1, and then f sub n minus 2, and then plus f sub n minus 1. So comma, 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 comma. Okay, so the first term, the Fibonacci number is equal to this value if n is actually less than or equal to -1. This is 0 if n is equal to 0. It's 1 if n is equal to 1. And then it's equal to f sub n minus 2 plus f sub n minus 1 if n is greater than or equal to 2. Okay, so we use that little definition, and then we're actually going to observe a little pattern here. So we see that we have a phi, and then plus 1 times phi plus 0. Okay, then we have a phi plus 1, and then we have 2 phi plus 1, then 3 phi plus 2, then 5 phi plus 3. You'll start to see that the constant correlating with the phi constant actually forms a little bit with the correlation with the Fibonacci, the definition with the Fibonacci sequence. So really, let's actually write this out. So let me write out the sequence of the Fibonacci numbers itself. So sequence of, I'm just going to abbreviate this Fn. So let's see, I'll start out with just the 3 dots first. And then we'll start off with, let's say we start off with -8, So then we use that formula, then it's going to be positive 5. Okay. Next out of that pattern would be negative 3. And then next out of that would be 2. And then negative 1. Then 1. Then 0. Then 1. Then 1 again. Then 2. Then 3. And 5 and 8. We start off with if n is equal to negative 1, then it correlates with this. Then subtract that from here. So 1 minus negative 1 is 2. Then negative 1 minus 2 is negative 3. Then 2 minus negative 3, positive 5, and so on and so forth. Go backwards. And then from the positive over here, we just start off with n equals 0. N is equal to 1. Then we start adding the numbers. 1 plus 1 is 2. Then 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. Then 5 plus 8, 13. Then so on and so forth. If we're noticing this little pattern here with correlation with the Fibonacci numbers associated with the phi constant, then we can actually define our general formula for our little sequences terms with phi. So therefore we can say that the explicit formula is phi sub n is actually equal to f sub n multiplied by phi, and then plus f sub n minus 1. And then that's for all, and then that's actually for all integers, for all integers n. So we have our little formula here. So that's so far that actually just defines, that's the formula we want from over here. Okay, so we have one side taken care of. So let's actually take an observation for the opposite side, which was for the root of 1 minus the square root of phi, and 5 divided by 2, which we said that that's equal to 1 minus phi. Okay, so now we're actually going to do the same method as before. So we say that this is equal to 1 minus square root of phi 2. That's part of the solutions from here, the two solutions. So next, I'm actually going to square both sides of the equation. So 1 minus phi square is equal to 1 minus square root of 5 divided by 2 square. Okay, and then I'll actually just do the direct calculations from here. So let's see, this is 1 minus square root of 5 divided by 2. Then multiply this a second time, 5 over here. And I just perform the FOIL method. So let's see, this is 1, then minus minus, so this is minus 2 times the square root of 5. Then we add that with 5, then divide by 4. We add the terms together. This is, let's see, 1 plus 5 is 6. Subtract that with 2, square root of 5, divide by 4. Some terms will cancel, so we get that this is 3 minus the square root of 5, and then all that being divided by 2. And so really, this can be rewritten as 1 minus the square root of 5 divided by 2, and then plus 1. And so therefore we can say that that's actually just equal to 1 minus phi and then plus 1. So therefore we can say that thus 1 minus phi squared is equal to 1 minus phi and then plus 1. And we'll just underline this little statement over here. And now next, what I want to do is perform the same method from previously. I'm going to multiply with actually instead 1 minus phi to the power n squared, or n minus 2. Okay, so then when I do this, I'll get, let's see, let me just go back to 1 minus phi n, and then multiply this with 1 minus phi to the n minus 2. It's actually 1 minus phi squared, then multiply with 1 minus phi n minus 2. And then we set that equal to, and then I set this equal to, let's see, phi, or supposed to be 1 minus phi, n minus 2, and then multiply with 1 minus phi plus 1. Okay, so when I do this, that means the 2's will cancel, so this is 1 minus phi to the power n, and then that's equal to, so let's see, we subtract the term by 1. So that means this is 1 minus phi, then n minus 1, then distribute over here, so this is plus 1 minus phi, then n minus 2. So now the next thing I want to do is, we're just going to do the same method as before, plug in our first phi terms and see like if there is a pattern that we can actually observe observe and then try to come up with an explicit formula just like from earlier. Yeah, I think I got room here. You know what, I'll move it over here. Is this fine? Yeah, okay. So if I plug 1, so let's see, 1 minus phi, then to the power 1, that's equal to 1 minus phi, then 1 minus 1, then plus 1 minus phi, 1 minus 2. So that's just equal to, let's see, this is just 1, and then plus 1 minus phi, inverse of that. So 1 divided by 1 minus phi actually has the property that it's actually just equal to negative phi. So this is negative phi, and so that's just equal to 1 minus phi, just from like the same thing given. Next, now we'll go to 2, then 1 minus phi, 2 minus 1 plus 1 minus phi, 2 minus 2, simply this is just 1 minus phi, and then plus 1 minus phi is 0, so yeah, this is just 1, so then we get that this is, for now I'll actually just leave it like that. I'm not gonna combine some terms just yet. For now I'm just gonna leave it the way it is. So let's go to 3. 1 minus phi, then 3, that's equal to 1 minus phi, 3 minus 1, then plus 1 minus phi, 3 minus 2. So then I have, that's a square, so that means this is just 1 minus phi plus 1, and then add that with, so that's 1, so it's 1 minus phi. Let's see if I can combine some terms. Let's see, they share a 1 minus phi, so this can be 2, let's see, 2 phi, or excuse me, what am I saying? 2 times 1 minus phi, and then plus 1. Okay, let's go to 4, then 1 minus phi, then 4 minus 1, plus 1 minus phi, then 4 minus 2. Simply, this is just 2 times 1 minus phi plus 1. And I subtract, and then I add this with, let's see, 2. We said that this is 1 minus phi plus 1. And so this is just 3 times 1 minus phi, and then plus 2. Is that correct? Yes. And then let's do one more. 1 minus 5, or 1 minus phi to the power 5. Man, that's a tongue twister. Then this is 1 minus 5 phi minus 1 plus 1 minus 5 5 minus 2. So this is equal to, let's see, that's 4, so 3, 1 minus 5 plus 2. Then add that with 3, which we said that this is 2, 1 minus 5 plus 1. And so we get that this is just 5, yeah, 5, 1 minus 5, and then plus 3. So we're starting to see some pattern here. It's just very similar to what we were doing over here. It's basically the same thing just as before, but we're dealing with, let's just for example treat 1 minus phi as some variable. And so you'll notice that we actually have a very similar pattern from coming from over here, and we can actually use that same formula from over here, but instead I'll substitute the phi with 1 minus phi. So therefore we can say that 1 minus phi and n is equal to capital F sub n multiplied by 1 minus phi, and then I add this with F sub n plus 1 for, or actually this is supposed to be a minus 1, and then that's for all integers. So we have our two little formulas now. That's pretty cool. Okay, so now the next thing is that we want to prove the following. So there's a difference of phi n minus 1 minus phi to the power n. So really what I want to do is I want to take the subtractions of our two formulas over here that we explicitly found. So therefore what I'll do is write it like this. So phi n, then subtract that with 1 minus phi n. Okay, so that's simply just equal to F sub n phi plus F sub n minus 1, write this in parentheses, and then subtract that with from over here. So this is F sub n 1 minus phi to the power, well, not power, just just 1 minus phi, and then add this with f sub n minus 1. And so you'll notice that the f sub n minus 1 cancel each other out. So what I can do is we have f sub n phi and then f sub n, so that means I can combine some terms. So let me just subtract this with f sub n and then plus f sub n phi. So therefore I have that, I can factor this out. So I have, this is f sub n and then multiply with 2 to the power phi and then subtract that with 1. Okay, and so what I'll do is I'll replace our phi with the golden ratio number. So this means I have f sub n, then multiply with 2 to the power, or 2 times 1 plus square root of phi divided by 2 plus 1. Okay, then moving on to that next line, the 2's cancel, and so we're left with f sub n multiply with 1 plus the square root of phi, then plus 1. Okay, and then just add the ones together. Actually, that's supposed to be a minus 1. Apologies for that. That's a minus, and then that's a minus over here. And you'll start to notice that all we're left with is just the square root of 5 times f sub n. Divide square root of 5 to both sides, and therefore we have the conclusion that, put this in a black box. Yep, y'all can see from here that f sub n is equal to phi sub n subtract with 1 minus phi sub n and then divided by the square root of 5, like so. Okay, and that's underlined in this orange box over here. Awesome. All right then, that's pretty cool if you ask me.